Limits of integration. Now, remember when we were working with indefinite integrals, we were essentially finding a family of functions, all the possible antiderivatives of a given function. We'd always add a plus c at the end, right? Well, definite integrals are a bit different. Instead of finding a general function, we're now interested in finding a specific value. We want to know the value of the integral, but only over a particular section of the x-axis. Think of it like zooming in on a specific part of the graph. And how do we define that specific section of the x-axis? That's where the limits of integration come in. These limits tell us exactly where to start and stop calculating the integral. They define the boundaries of the region we're interested in. We'll be diving deeper into exactly how these limits work in the following slides, but for now, just understand that they are crucial for turning an indefinite integral into a definite numerical answer. Okay, so let's move on to a new and very important concept in integral calculus: limits of integration. Understanding the notation. Okay, so now that we've discussed what limits of integration are and why we need them, remembering that indefinite integrals gave us a family of functions, but definite integrals give us a specific value, let's dive into the notation itself. This slide shows us how we write a definite integral mathematically. You'll see this symbol, and it's important to get familiar with it. It looks like a stretched out S. We read this as the integral of. Now, let's break down everything within that integral sign. We have the integral of, followed by a function, which we call f of x, so f of x is the function we want to integrate. It's what we're working with. We call this f of x the integrand. Think of it as the thing being integrated. Next, you'll see dx. This isn't just some random addition. The dx tells us with respect to which variable we are performing the integration. In this case, it means we are integrating with respect to the variable x, so we're looking at how the function changes as x changes. Finally, we have the numbers a and b positioned at the bottom and top of the integral sign, respectively. These, as we've already touched upon, are the limits of integration. We'll be exploring these in more detail, but remember they define the interval over which we are calculating the integral. We'll see in the next slides how these limits act as boundaries for our calculation, defining the specific portion of the x-axis we're interested in. So, putting it all together, this notation, integral of f of x dx with limits a and b, is the standard way to represent a definite integral, and understanding each part is crucial for successfully evaluating these integrals. The lower and upper limits. The first line here tells us that the limits of integration essentially act as boundaries for our calculation. Think of it like drawing a line on the x-axis. The limits tell us where to start and stop considering the function. Now let's look at part A, the lower limit. This value, which we denote as a, is always written at the bottom of the integral sign. Remember the notation we covered? The integral sign, then a value at the bottom, then dx, and finally a value at the top. This bottom value, a, is what we call the lower limit of integration. It represents the starting point of the interval we're interested in on the x-axis. So, if we're looking at the area under a curve between 2 points, a is where we begin. Now let's move on to part B, the upper limit. This value, denoted as b, is written at the top of the integral sign. It's called the upper limit of integration, and it represents the ending point of the interval on the x-axis. So, b is where we stop considering the function. Okay, so let's move on to slide 3, where we'll really nail down what these limits of integration mean. As we discussed on the previous slides, indefinite integrals give us a family of functions, but definite integrals give us a specific value. And that specific value is determined by these limits. Think of it this way: a is the left boundary, and b is the right boundary of the region we're analyzing with the integral. We'll see in the next slide how these two limits together define a specific interval, and how that interval is crucial for getting a numerical answer from our definite integral. It's important to keep these straight, as swapping them will change the sign of your answer, as we'll cover in the common mistakes slide. The interval of integration. Firstly, it states that together, the lower limit a and the upper limit b define a closed interval, written as a bracket b. Think of it like drawing a line segment on the x-axis. A is where the segment starts and b is where it ends. The brackets signify that we include both a and b in our consideration. It's a closed interval, meaning it includes the endpoints. Next, it says, when we evaluate the definite integral a to b of f of x dx, we are essentially analyzing the behavior of the function f of x only for values of x that lie between a and b, inclusive. So, when we put those limits on the integral, we're not looking at the entire function f of x, we're specifically focusing on what the function is doing within that interval we just defined, from a up to and including b. Everything outside that range is irrelevant for this particular calculation. Finally, and this is a really important geometric interpretation. Geometrically, if f of x is positive, this integral represents the area under the curve f of x bounded by the vertical lines x equals a and x equals b. Imagine the graph of your function. If the graph is above the x-axis, meaning f of x is positive, then the definite integral gives you the area of the region trapped between the curve, the x-axis, and those vertical lines at x equals a and x equals b. This area is what we're calculating with the definite integral. Okay, let's move on to slide 4. As we've discussed in the previous slides, the limits of integration are crucial for definite integrals. Now, this slide explains how those limits actually work together. Keep this geometric idea in mind, as it will be very helpful when we start actually solving definite integrals. And remember, in the next slide, we'll see how this all applies to a real-world example, so it's good to have a solid understanding of these concepts first. Real-world example, calculating total distance. Okay, so now that we've covered what limits of integration are and how the notation works, let's solidify our understanding with a practical example. This will help you see how these concepts apply to real-world problems. We're going to look at a scenario involving physics. Imagine a car moving, and its velocity is described by a function. Specifically, let's say the car's velocity, which we'll denote as v of t, is equal to 3t squared meters per second. Remember, t represents time. The question is, how can we determine the total distance the car traveled between the second and fifth seconds of its journey? That's where definite integrals, and crucially, the limits of integration come into play. Let's break this down step by step. First, we need to identify the function we're going to integrate. In this case, it's the velocity function, v of t, which is 3t squared. Next, we need to pinpoint the starting point of our journey segment. The problem states we're interested in the time between the second and fifth seconds, so the journey begins at t equals 2. This value 2 will become our lower limit of integration, which we typically label as a. So, a equals 2. Similarly, the ending point of our journey segment is at t equals 5. This value, 5, will be our upper limit of integration, labeled as b. Therefore, b equals 5. Now we can set up the definite integral. We take the integral symbol, and then we place our lower limit, 2, at the bottom, and our upper limit, 5, at the top. This gives us the integral from 2 to 5 of 3t squared dt. Remember, the dt indicates that we are integrating with respect to the variable t. So, the entire expression looks like this, the integral from 2 to 5 of 3t squared dt. In this example, the limits, 2 and 5, aren't just numbers floating around. They precisely define which portion of the car's entire trip we are analyzing. We're not looking at the entire journey, we're focusing specifically on the time interval from 2 seconds to 5 seconds. This is a key concept to remember. The limits of integration allow us to isolate and calculate quantities, like distance traveled, over specific intervals. We'll see how to actually solve this integral and find the numerical answer in the next few slides. But for now, it's important to understand what the integral represents in this context and how the limits define the boundaries of our calculation. Common mistakes to avoid. First, let's talk about swapping the limits. It's very common for beginners to accidentally reverse the order of the lower and upper limits of integration. Remember, the lower limit, the starting point of our interval, always goes at the bottom of the integral sign, and the upper limit, the ending point, goes at the top. So, if you see an integral written as integral with a at the top and b at the bottom of the integral sign, integrating a function f of x with respect to x, that's a red flag. If you do swap them, it doesn't make the integral unsolvable, but it will change the sign of the answer. Specifically, the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Essentially, you'll get the same area, but with a flipped sign. Keep that in mind. Next, let's address confusing limits with variables. This is a subtle but important distinction. The limits of integration, a and b, are constants, they are just numbers. They define the boundaries of the interval we're interested in. They are not variables like x or t that can change within the integral. Think of a and b as defining a specific window through which we are viewing the function. We're not integrating over all possible values of x, only those between a and b. Finally, ignoring the interval. Some students treat the limits of integration as if they're just decorative elements of the integral. But they are absolutely crucial. The limits fundamentally change what the integral means. Remember from our earlier discussion that an indefinite integral, one without limits, gives you a family of functions, represented by something like x squared plus c. However, a definite integral with limits of integration gives you a specific, single numerical value. It's the area under the curve, or the accumulated quantity, within that defined interval. So, don't underestimate the power of those limits. They're what turn a general antiderivative into a concrete answer. Okay, let's move on to slide 6, where we discuss some common mistakes students make when working with definite integrals. It's good to be aware of these before you encounter them in your problem solving, so you can avoid them altogether. Alright, that covers the common pitfalls. Now, let's move on to the final slide, where we'll recap the key takeaways from this entire discussion. Key takeaways. First, regarding notation. Remember that integral symbol and the expression we've been working with, integral a to b of f of x dx. In this notation, a and b are what we call the limits of integration. They are crucial because they tell us where we are calculating the integral. Next, the lower limit. The value a, which sits at the bottom of the integral, represents the starting point of our integration. Think of it as where we begin to accumulate the area, or in the case of our velocity example, where we start measuring the time. Then we have the upper limit. The value b, positioned at the top of the integral, marks the ending point of our integration. It's where we stop accumulating the area or measuring the time. Now consider the interval. Together, the lower limit, a, and the upper limit, b, define a closed interval, written as a bracket b. This means we are only interested in the function f of x for values of x that fall between a and b, including a and b themselves. This interval is the specific section of the x-axis we're analyzing. Finally, and this is a really important distinction, the result. Unlike indefinite integrals, which give us a family of functions plus a constant, c, definite integrals, those with limits of integration give us a single, unique numerical value. This is because we're calculating something specific within that defined interval. Remember, we're often finding an area, a distance, or some other quantifiable amount over that specific range. Okay, let's recap everything we've learned about limits of integration with these key takeaways. So, keep these points in mind as we move forward. Understanding these limits is fundamental to successfully evaluating definite integrals and applying them to real-world problems.